नमस्कार, सुस्वागतम, आदाबर्स, केम छो, गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, for the PRL का अमृत व्याख्यान. Today is the 52nd व्याख्यान of the 75 episode series of व्याख्यान्स, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL का अमृत व्याख्यान. Today, we have yet another very distinguished व्याख्यानकर्ता, Professor Yashwant Gupta with us, who is the director of the National Center for Radio Astronomy in Pune. And he will be giving the व्याख्यान on the title Probing the Universe with Radio Waves, Landmark Achievement in India over the years. We greatly appreciate and thank Professor Gupta to be with us today and accepting our invitation to deliver today's व्याख्यान. I would now request Professor Nandita Srivastava to kindly introduce our today's व्याख्यानकर्ता to our audience at the WebEx panel as well as at the PRL's YouTube channel. Over to you, Professor Nandita.
Thank you, Professor Bharadwaj. It is indeed my pleasure to introduce Professor Yashwant Gupta, Distinguished Professor at Tata Institute of Fundamental Research, TIFR. He is the Center Director of TIFR's National Center for Radio Astrophysics, NCRA, located in Pune. Professor Gupta obtained his MS and PhD in radio astronomy from the University of California, San Diego in 1990. After completing his bachelor's degree in electrical engineering from Indian Institute of Technology, Kanpur in 1985. In addition to research on pulsars, the rapidly rotating, highly magnetized neutron stars, Professor Gupta has also made significant contributions to instrumentation and signal processing applications in radio astronomy. He has contributed extensively to the building and running of the Giant Meter Radio Telescope Observatory, a world-class facility located about 80 kilometers from Pune, which is built and operated by NCRA. He also spearheads India's participation in the ambitious Square Kilometer Array SKA project, an international collaborative project to design and build the next generation global radio astronomy facility. Professor Gupta has been conferred the Shanti Swarup Bhatnagar Prize in Physical Sciences in the year 2007. He has been elected a Fellow of the National Academy of Sciences of India and also of Indian Academy of Sciences. I would like to thank Professor Gupta for readily accepting our invitation in spite of his busy schedule and gracing our celebrations of PRL at 75. I cannot thank him enough for keeping his promise today, although I know he is unwell today. We are looking forward to Professor Gupta's talk on very interesting topic. As Professor Bharadwaj already mentioned, probing the universe with radio waves, landmark achievements in India over the years, which is indeed a reason for all the Indians and astronomers in particular to celebrate Azadi Ka Amrit Mahotsav in its true spirit. With these words, I now invite Professor Yashwant Gupta to deliver the 52nd Amrit Vyakhyaan of PRL. Professor Gupta, please.
Thank you so much. Thank you for the kind words and for inviting me to join your special series celebrating this very historic landmark that our country is going to reach in a few weeks. It's a pleasure to join you all. And let me just get my screen sharing working. Right. I hope you can see this.
Yes, we can see.
Okay. And so what I will be talking today is, as the title says, probing how we study the universe with radio waves, and then bringing out some of the landmark achievements that have happened in our country almost since independence, actually. I know I'm speaking to a fairly wide audience, which are not all astronomers, a mixed audience, and I'm also hoping that this is reaching out to the younger community of students and others who are interested. So I will cover some basics, some background, which to my esteemed hardcore astronomy colleagues may sound a bit boring in the beginning, but please bear with me. It will be useful to set the background for everybody. So I will actually start right at the beginning. As we all know, astronomy is the oldest science generally recognized. Started with us using our naked eyes because that's where we have the natural detectors for light waves and doing all the processing in the human brain. But we know that this evolved dramatically from the time Galileo turned the telescope to the heavens and just completely revolutionized the way we see astronomy. And if you just track the growth of telescopes, optical, from the time of Galileo, you'll see that they have grown in size, complexity, and reaching to the huge structures that we build today. And there's obviously the trend here that bigger is better. And it's worth asking that what is it that we get better when we build the bigger and bigger facilities, because this is something that will carry over to how we build radio telescopes also. And I think many of you will know this, that there are two main drivers. One is that the bigger the telescope, the more sensitive it is because it has a larger aperture and it can collect more light. The other one, which again many of us recognize, is that the bigger a telescope is, the better is the resolution, which goes inversely as the size of the aperture and also on the wavelength, which means that a bigger aperture can resolve or separate out closer by objects in the sky as measured by angular separation in the sky. So the thing to note, of course, is that both of these depend on the size of the aperture, and that's why it's the main driver to build the big telescopes. And just to illustrate this with this very simple example, which will appeal to all of us, if you look for the Andromeda galaxy with the naked eye in very good seeing conditions, you will see something like this, small blurry patch. And as you put bigger and bigger optical telescopes to look at it, you will start seeing the benefits of both sensitivity, fainter and fainter objects becoming visible, and resolution, where you start separating out the details and seeing more of the detailed structure of the source that you're studying. Of course, as we know, that the optical is just part of a large spectrum of electromagnetic waves. And so the natural question to ask is that if we can see objects in the universe at optical, can we see them at other wavelengths? And there are a few interesting questions that one could ask as listed here. That can you see the same object in different parts of the electromagnetic spectrum? Do different wavelengths give us different or complementary information about the object? And are there some objects or phenomena which can be studied only at some particular parts of the electromagnetic spectrum? And the answer to all of these is yes. And so that is something that motivates this, the search for being able to do astronomy at other wavelengths. And again, I will just illustrate this. This is just for the latest of the knowledge that we have of being able to observe at different wavelengths. The same Andromeda galaxy, as seen in the optical picture that I showed earlier, and then seen at other different parts of the electromagnetic spectrum. And again, you can see the points that we talked about, that different parts of the electromagnetic spectrum give you complementary view of the same object. You learn different parts of it. There are some parts which are not visible in certain wavelengths, and there are some parts which are more prominent at some wavelengths, and this is what the modern astronomer does to put together the information from all the wavelengths to get the best possible understanding of the astrophysics involved. Now coming back then to ask that what is it that was required to do multi-wavelength astronomy? Obviously, as we saw, that we need the detectors, just like we have the natural detectors for optical wavelengths. And this, of course, happened with time, with technology, as we learned to build things, whether it is photographic plates or charge-coupled devices or radio communication equipment, which all provided different ways of detecting electromagnetic signals. Second, of course, is a hurdle which was soon realized, that not all of the electromagnetic radiation from outer space does reach us. And this is shown by a plot like this, which measures the opacity of the Earth's environment as a function of wavelength in the electromagnetic spectrum. And what you want is very low opacity, that is, the signal should reach us from outside to the surface of the Earth. And as you can see here, that there are two main windows where the opacity is good enough or low enough for observations to be done with ground-based facilities. One is in the optical band, which is where astronomy started. The other one is this large window, which lies in the radio band. And this is, therefore, what one would expect to be the next branch of astronomy to develop the moment one learned how to be able to handle radio waves, so to speak. And that takes us to a small detour into the whole business of how radio waves were first, um, you know, understood, and then tools were developed to detect them. So starting from Maxwell, who developed the theory that predicted electromagnetic radiation at all the wavelengths that we just talked about, to Heinrich Hertz, who proved that radio waves predicted by Maxwell do exist, but he didn't think that they were of any practical use, and he didn't follow it up. And then it took two people here, our own J.C. Bose and Marconi, to actually demonstrate for the first time that you can both generate and detect radio waves under your control, which then led to the whole phenomena of the communication technology that we are so used to today. And so it was actually, though for a long time people thought that Marconi was the inventor of this techniques, it was actually J.C. Bose who showed for the first time back in 1894 that how you could both generate and receive radio waves. And he did this in Kolkata at a frequency of 60 gigahertz about a year before Marconi, and it is now formally, officially recognized by the IEEE that J.C. Bose was the pioneer in this field, where the first millimeter wave communication experiment. And so this is an IEEE milestone. It's a special recognition that the IEEE gives for worldwide achievements of importance in not just radio communication technology, but even allied fields. And we'll see a bit more of it later on. But it's a matter to take note that this is something. So we today we are talking about 75 years, but we can actually go back and celebrate all the way to 1894 when Acharya J.C. Bose first demonstrated how you could receive radio waves. From Bose and Marconi, we know how communication technology went, but to get to radio astronomy took a few more years because the detectors that these were built for the communication technology weren't in the beginning quite sensitive enough to detect the radio signals from outer space. And in fact, it so happens that the discovery of radio signals from celestial objects happened by accident, serendipitously, when a piece of transatlantic communication equipment was being debugged for some extra noise that it was producing. And so it was Carl Jansky in Bell Labs who was given the task to understand why there was unwanted hiss or noise coming in this sensitive equipment that they were building to transmit signals across the Atlantic. And he built this contraption, which does not look like a radio antenna, but is actually the first radio telescope in the world, which he put on a rotating carousel and pointed in different directions to try and find out the source of the unwanted noise. And to his surprise, he found that this noise was coming not from a fixed location on the earth, but from a fixed direction in the sky, and that it was therefore a celestial radio source that they were seeing. So that is how radio astronomy was born and kicked off. And note the years, this is 1940s that we are talking about. And it was in the early days, it was pioneered by radio engineers working in their spare time to build equipment whereby they could pick up these much fainter signals and be able to try and understand where these sources were coming from. It took a while for the regular astronomy community to take notice and realize that there was this new branch of astronomy which could provide very vital and complementary information to what they were used to with their large optical telescopes. And so this is, in fact, the first radio map of the sky made in 1940s by Grotreber, showing the main strong sources, most of them in the plane of the Milky Way galaxy, but also containing some extragalactic sources over here. Sagittarius A star, I think some of you may have followed the second black hole shadow detection, which is a Sagittarius A star, center of our galaxy, one of the strongest radio sources that is seen. So moving from there, we would want to understand just a few basic things about radio telescopes before going on to see how the scene was in India. One is just to keep in mind that the basic idea of a radio telescope is not too different from, say, your favorite satellite dish, where the signals coming are focused from a parabolic antenna to a feed antenna. The feed antenna converts that electromagnetic signal into a electrical voltage, which is amplified, filtered, shaped, and so on, and finally detected into a signal that you can understand, which contains the information of interest. There are two main differences. One is that the signal levels that we deal with in radio astronomy are much, much, much weaker than the signals that we get in all our terrestrial transmissions. And in fact, the kind of units that we use, depending on if you're comfortable with the physics background, 10 to the minus 26 watts per square meter per hertz is the kind of power levels that we are getting from a typical source in the sky. If you're more comfortable with electrical engineering, that's minus 100 dBm power level. And so what this leads to is this challenge to get enough sensitivity. That means to be able to collect enough of this weak signal to overcome the noise that is always present in any receiver electronics that you build. You have to build very large antennas, much, much larger than this simple satellite dish receiver. And we also have to build very high quality, low noise electronics to minimize the unwanted self-generated noise and have a good chance for detecting the weak signal. The other thing that is different compared to man-made transmissions is that most of the astronomical sources are usually wideband sources, not all. There are spectral line sources, but often you can make the observation over a very large bandwidth in order to improve the amount of signal that you're collecting. And so we tend to nowadays do observations with hundreds of megahertz of bandwidth. And the last part is that unlike man-made signals, these natural sources are, of course, statistically by and large constant, except nowadays the transient universe throws up many short duration transient sources. But if you are observing a galaxy, it looks the same over the few seconds, minutes, hours, years, thousands of years, and so on. So you can actually do an observation over a long time duration, which means, again, you collect more power. And it can be shown that the noise does not grow in the same manner as the signal as you integrate longer and longer. There is a square root of time difference in the way the noise and signal grow. And therefore, you gain in signal to noise by increasing the bandwidth and the integration time of the observation. So all of these are the techniques that we use in order to get sensitivity. As you remember, the other thing I mentioned is the resolution. And in resolution, again, radio astronomy suffers a big hit because if you remember the formula for resolution, it goes as wavelength and the aperture size. So our wavelengths are much, much, much larger than the optical wavelengths. And so if you are at a observation of 1 meter wavelength, which is 300 megahertz frequency, and you have a 100-meter size antenna, which is quite large, you will get a resolution of half a degree. And half a degree is a very poor resolution. Half a degree is the size, angular size of the moon, for example. So which means that if you turn a radio telescope of this kind towards the moon, you would just see a blurred image, no details, because you don't have enough resolution. So that's obviously not good enough for being complementary to optical telescopes, which can obviously give you much higher resolution. And so you would say, well, can you build much bigger? It's much harder to build much bigger, larger antennas. And so the way radio astronomers solved this problem is to come up with a technique which is called aperture synthesis. And in aperture synthesis, it was shown that in order to build an antenna, which is it is not necessary to completely fill the aperture, but you can build smaller antennas and spread them out over the entire region that you would have liked to cover with a single dish, and then combine the signals in an appropriate manner and recover an image which has the resolution that you would have got pretty much with a dish whose size was equal to the largest separation between the individual antennas in the array. So in the resolution formula, we end up replacing the size of the individual large dish with the largest separation between the antennas, which is something that you can control more easily as long as you have enough place where you can keep the antennas, and thereby you can increase the resolution. This, of course, requires the extra complexity of having to bring the signals together from the antennas to a common place and do the processing, which is specialized processing required for this aperture synthesis, which increases the complexity of the electronics manyfold. But that is manageable compared to the sheer cost of building very large single dish antennas. So as a result, all modern telescopes today are large arrays of antennas. And the difference in terms of, again, the quality of the image that you can get is just shown by this example of radio galaxy, where the image made in the early days with a single dish telescope and the image made with one of these aperture synthesis arrays. This is now 1980s kind of situation, and you can see the improvement in the resolution and the ability to detect the finer details. So with that brief background to just bring you all reasonably up to date with what we do in radio astronomy, I will now move on to talk about what have been the achievements in radio astronomy in India. So, as I mentioned, radio astronomy started in the world in the 1940s, but you'll be surprised to know that in the 1950s already, there were the first radio astronomy observations in India. So, and that credit actually goes to the Kodaikanal Solar Observatory, which is a historical observatory in the country, which had been operating for 50 years, even in 1950. And the first time a radio astronomy observation was done was with a 100 megahertz Yagi antenna setup put over there to study the sun. And so this is the report of that first observations, and it talks about the equipment being installed at the Kodaikanal Solar Observatory. This is A.K. Das, 1950. From that experimental setup where the radio noise burst from the sun was detected corresponding to a prominence eruption of a prominence dating to February 1953. In the initial years, there was further activity that happened at the Kodaikanal Solar Observatory to build further, slightly more sophisticated radio telescopes. And the group set up VHF system working at 200, 160 megahertz. And this is a block diagram of the kind of radio receiver setup that they made at that time. And it also included so the aperture synthesis technique that I described is also called interferometry. I probably glossed over that. So the technical term that we often use is the interferometer as compared to an aperture synthesis instrument. So they also did the first two-element interferometer, just correlating signals from two different antennas. And it was interesting that they were able to build receivers with good sensitivity and stability at that time, though we will find it a bit surprising. So maybe not surprising, but just interesting that this is the one of their RF amplifiers. And as you can see, these are devices of that generation. The things that we will in our generation obviously don't see anymore. But even with these, there was fairly good quality results obtained from both the single experiment and the interferometer. This is a measurement of quiet sun versus the disturbed sun. Signals clearly seen. And so a lot of this was focused on solar studies in the beginning, also interplanetary scintillations, and some amount of scintillations of extragalactic sources. And there was also the first attempt to build a parabolic dish, 20-foot paraboloid that was built there and made operational. From there, the first dipole arrays came up. So the first of these arrays as I said, a lot of the astronomy was being done with the arrays. So 36 dipole antenna array working at very low frequency, 25 megahertz, one of the lowest that radio astronomy was being done, was again set up at Kodaikanal by IIA, and it was used for studying solar bursts by CHV Shastri, and they followed it up for many years with few interesting results that came from that. Here's a sample of isolated solar bursts detected with that equipment in the 1960s. In the 1970s, the IIA and the RRI jointly set up a larger radio telescope dipole array called the GT telescope, which was operating at 34.5 megahertz, slightly higher than the 25 megahertz of the original array. And it had many more dipoles, 1,000 dipoles in a T configuration. So you can see a picture here. These line that you see is a line of dipoles forming one side of the T configuration. And so you can see 1.4 kilometers by 0.5 kilometers in dimensions. And this was again used for study of the sun and other diverse objects in the sky. In fact, it was also later on used to make an all-sky map using this aperture synthesis technique that I described. So this was one of the first all-sky maps at 34.5 megahertz frequency, driven largely by colleagues at the Raman Research Institute. And though it was published a few years later, but a lot of this work was done with the GT radio telescope. From there, based on this experience, IIA also built a dedicated radio heliograph array. So this was another dipole array. Now you can see the dipoles more clearly. These are the individual dipoles of the array. And this was used, again, dedicatedly for studies of solar corona at a range of frequencies, so much more versatile in terms of frequency coverage, 40 to 150 megahertz. And this was made operational in the 1990s and has been in good service, producing interesting results. One example of a composite image combining the Gauri Bidnoor radio heliograph and with the other observations. And this is something that has been a fairly unique facility and doing very good science. One further development of the dipole arrays is an interesting experiment, which is the first time when groups from India have gone and built a facility outside India. So this is what is called the Mauritius Radio Telescope. Unfortunately, no longer active now. The MRT was again a dipole array. Here the dipoles are different. You can see these are helical dipoles, but again in a T kind of configuration with the distributed in a manner which again allows you to get good aperture synthesis capabilities. This was built to operate around 150 megahertz, and again it was used by groups from the RRI, IIA, and the University of Mauritius to do an all-sky imaging similar to this 34.5 megahertz all-sky imaging that I talked about. And though short-lived, this was an interesting experiment in terms of how you can conceive of a facility and build it in collaboration with collaborators outside. Then there was the first millimeter wave attempts in India that I should mention. All this while I've been talking about radio astronomy being done at very long wavelengths, meters wavelengths, and this was perhaps the one and only attempt made in India to develop millimeter wave radio astronomy. It was done by the Raman Research Institute in the 1980s. It was a strong initiative of Prof. V. Radhakrishnan, whom we all remember as RAD. It was a 10.4 meter antenna working at a frequency of up to 100 gigahertz, that is 3 millimeter wavelength. And these kind of frequencies require cryogenic receivers. So you remember, I talked about noise from the receiver system, and in order to reduce the noise, when you really want to reduce it dramatically, you have to cool the receiver to cryogenic temperatures. And in high frequency radio astronomy, you often require that because you're fighting against very low amount of signal from the sky. And so this was also developed for this telescope for the first time and used. And it was aimed at observations of carbon monoxide emission from molecular clouds and masers, methanol masers and SiO masers. And though it was, it produced a few results, but was not a very successful venture in the long run. Today, it's heartening to note that there are plans for a sub-millimeter telescope to be built in India, which is being led by ISRO, and we look forward to India getting some capability in the very high high frequency part of the radio spectrum. So, while talking about the Raman Research Institute, I should mention about the SARAS experiment. It was a cosmology experiment, and this is another very different kind of a landmark achievement. I won't go into the details of what this means, but this is the attempt to detect the global epoch of reionization signal. That is the signal that we expect to see when the first stars and galaxies form and the universe gets reionized from the dark ages. And there's a well-defined theoretical expectation of what you would see under certain conditions of the understanding of the cosmology. And a lot of groups around the world have been trying to build experiments which will try to detect this kind of a signal. And this requires very specific kinds of technologies. Again, I won't go into the details of how the antenna technology was developed, from initially being ground-based, then finding that the best thing to do is to put this antenna on water in order to minimize the unwanted pickups and so on, and designing the corresponding electronics to be matched with the sensitivity required to do this. And all this finally has led to a very recent result in Nature Astronomy just earlier this year, where they have put out results using the SARAS-3 experiment, which actually refute the findings from an earlier experiment called the EDGES experiment from 2018, where they claimed to have got the first detection of this EOR signal. And so this is a very interesting field, and there is a good possibility for landmark contributions further from India. Okay, I'm sorry, I missed a slide in between. I don't know where it went. I did have a slide to talk about what has been done at PRL in terms of the three-station IPS and the work done with the Thaltej array. And I'm really sorry, it was supposed to be a little bit earlier when I was talking about dipole arrays. So apologies, but I think that is something that colleagues at PRL would be fairly well aware. But there was very good work done in interplanetary scintillation studies with a three-station IPS setup, which had arrays at Thaltej, Surat, and Rajkot, and professors Alurkar and others, Mosley and others, who did a lot of work in the early years. And the Thaltej array was the biggest one, which survived for quite some time and was used for further different kinds of scintillation studies by colleagues at PRL. And amongst the ones who may still be there is Professor Janardhan, who is an old colleague who also was involved in some of the experiments. And we do look forward to PRL picking up the thread again in terms of radio astronomy experimentation. With that, I'll turn to the work done by our group at TIFR, which owes its origin to Professor Govind Swarup, who was one of the founders of radio astronomy in the country. And this dates back to 1961, when Professor Swarup, after finishing his training in Australia and in US, was invited by Homi Bhabha to come and set up a radio astronomy group at the TIFR. And so this is correspondence from the early 1960s. And Professor Swarup joined in 1963 and set up the radio astronomy group, and got going with various kinds of projects. And I'll just give a highlight of some of the important things. The Kalyan radio telescope. So Kalyan is the same Kalyan that we know, the suburb of Bombay, where if you were to think today, can you have a radio telescope in the concrete jungle? Well, there was a time when there was a radio telescope there, and it was the first of the dish arrays. So I talked about dipole-based arrays done by colleagues from IIA and RRI, as well as from PRL. This was the first array made using dish antennas. So as you can see here, small dish antennas. These were actually acquired from radio astronomy colleagues in Australia and set up in Kalyan to make north, south, and east, west. Again, this same T geometry of the array, except that now we're working at a much higher frequency, 600 megahertz. And this was, but again, originally designed and dedicated for solar astronomy. So as you can see, solar astronomy was one of the driving forces for the early developments of radio astronomy in the country. It was used for studying the quiet and active sun at 600 megahertz, and it produced some interesting results on solar limb brightening and interpretation of the million-degree temperature of the solar corona and so on. From then on, the next landmark achievement of the group was the Ooty radio telescope, which many of you may be aware of. It was conceived in the 1960s, and the motivation here was to use the technique called lunar occultations to provide the accurate size and positions of a large number of radio sources and to test cosmology models. So that's quite an interesting thing, a technique called lunar occultation, which is basically when a bright source is occulted by a disk like the moon, and when it emerges from the occultation, there's a diffraction pattern that is produced, and that radio signal of that diffraction pattern, if you can pick that up, it will give you information about the angular size of that source, which is being occulted by the lunar disk. And so it's, as you can see, it's a very indirect way, but a very innovative use of radio astronomy to try and measure the angular sizes of very far away galaxies and quasars in order to test the models of cosmology. So in order to do this, what was built was this telescope. It's a long cylindrical paraboloid, which means that the reflecting surface is a parabola, and it's in this direction. It is about 30 meters wide, and the length of the parabola is 530 meters long. And it is, as you can see, it's positioned on the slope of a hill, and this was done in order to make it an equatorial mount. An equatorial mount means that you have to steer the telescope only along one axis in order to follow an object in the sky as the Earth rotates. And in this case, the slope of the hill was chosen to be equal to the latitude of the place where it was located. So by doing this, you align the long axis of the telescope along that, and then you have to only rotate the telescope along only the long axis in order for the entire focus line of the telescope to be seeing the same source as the Earth rotates. Of course, in this dimension, which is the declination direction, you track the source by steering the beam. So there's beam forming that you have to do by picking up the signals from all of these dipole elements that are placed at the focus line of the paraboloid. And this gives you the equivalent of a 130 meter size dish. So you can see already that's large. We were talking about 100-meter size antennas as some of the largest that are fully steerable. And by doing this trick, one could make it a reasonably light structure. And as you can see, it does not have a solid reflecting surface. There is a grid of wires, you can just about see that, which reflects the waves, which are at 1 meter wavelength, 327 megahertz. And this telescope was built and made operational in 1970, and it did actually make these measurements that it was meant to do, and it provided evidence in favor of the Big Bang model as compared to the steady state model of the universe. They were actually Professor Sarup Kapai and others were actually able to measure these angular sizes of the sources as a function of their redshift, that is the distance, and come up with this conclusion. In addition, of course, a telescope like this contributed to many other areas of astrophysics. So this is now that regime where you build a facility that is sensitive enough and powerful enough that instead of just being doing one or two specific science goals that was originally thought about, it is found capable and useful of carrying out many other different kinds of explorations and investigations. So the ORT has been used for all kinds of studies of radio galaxies, quasars, pulsars, radio recombination lines, interstellar, interplanetary plasmas, and so on. And this is just one example. A lot of the interplanetary scintillation work, which I talked about that being done by the PRL three-station IPS setup. This was a single-station IPS observations, and techniques were devised how to measure the solar wind from single-station IPS observations by colleagues at NCRA. And but in addition to that, there was this kind of long-term monitoring of the solar wind. And there's an example where there was a clear evidence shown of the steady decline in the density turbulence of the solar wind over several solar cycles. And so there was interesting kinds of studies done with the ORT. And the interesting thing is that it is still functional after 50 years. And not only that, we are actually upgrading it to make it a more powerful and versatile facility by redoing a lot of the electronics and the way the signals are combined from that array of 1024 dipoles at the focal line of the paraboloid to make it a more powerful telescope with a lot of digital signal processing added to do that. After the Ooty telescope was built and operational for some time, the next landmark that the group achieved was to build the first proper synthesis radio telescope, which is as I was mentioning, the ability to put antennas at different locations and be able to collect the signals from them, combine them, and do this interferometric or aperture synthesis technique. And in this case, this was an extension of the Ooty telescope, the Ooty synthesis radio telescope, where in addition to this long Ooty telescope, there were several baby cylinders, is what they were called. The Ooty was a large, big cylindrical paraboloid. These were smaller cylinders that were added at different distances, covering a region of 4 kilometers by 2 kilometers, and again operating at the same frequency of 327 megahertz. And this produced interesting images now of different objects in the sky. So now you can make higher resolution images, and these are various just a snapshot of some of the interesting discoveries or studies that were done with the OSRT of various kinds of radio galaxies mostly. But this also gave the experience of how to build such large interconnected synthesis telescopes. And that led to the next big step, which is one of the biggest landmarks in the growth of radio astronomy in the country, which is the Giant Meter Wave Radio Telescope. This was motivated in the 1980s after the OSRT was sort of working, and people understood how to do these things. And it was basically the aim was to build a world-class synthesis telescope at low frequencies. And low frequencies means, again, from say of the order of 100 megahertz up to 1.5 gigahertz, because most of the aperture synthesis instruments in the world were getting built at the higher frequencies, and there was a niche where lots of new results and discoveries were thought to be possible at low frequencies. And so the first concepts in the 1984 started based on the Ooty experience to design it with large cylinders. But soon it was realized that due to various reasons, it's better to go to parabolic dishes. And so the original plan was 34 dishes of 45 meters. And by the time the proposal was finalized and the funding was secured, finally it came down to 30 dishes being built. And the construction started in 1990. The first antenna was erected in 1992, and the first light observations happened in 1997 to 1998. And it was completed and released for worldwide use in 2002. And so we just completed 20 years of operation last year. And we also did a major upgrade of the facility which was completed around 2019, which further improved its capabilities. So I'll describe briefly what the Gmrt is and how it works and what we do with it. So as I said, there are 30 dishes, each of 45-meter diameter, which is quite large, and they're spread out over a 30-kilometer region. So in the is about 80 kilometers from Pune. As you go from Pune to Nasik, you cross through the array. There are 12 antennas in a central 1 kilometer by 1 kilometer compact region, and the remaining 18 are spread out in these roughly Y-shaped structure, 6 antennas in each arm, extending to about a little bit over 14-kilometer radius from the center. And so this allows you to synthesize an antenna of 30-kilometer diameter as far as the resolution is concerned. And originally, when the Gmrt was built, it was meant to cover 5 different radio frequency bands. So now, once again, you can see that this is the movement from specialized single-purpose instruments to general-purpose large facilities which can be capable of different kinds of science. So it was designed to have 5 different frequency bands covering this range of frequencies, and there were some good reasons to choose these specific bands, and a maximum instantaneous bandwidth of 32 megahertz, which is again quite large for that time. And so effectively it had a very large collecting area, and it was also a lot of foresight that went into it to design it to support the interferometry or aperture synthesis mode, which I have talked about quite a bit already. But the other mode, which I did not talk about at all, which is very useful for studying compact objects like pulsars, which is called a beamformer mode, where you just add the signal from all the antennas without doing the complicated signal processing that is required for interferometry. You don't get that resolution, but you can get the full sensitivity and very high time capability, which is important for studying transient signals. So this is just a view. If you Google, you will see this. This is the central 1 kilometer by 1 kilometer. You can just about make out some of the antennas there. And this is just a zoomed in view. And these are the three of the closest antennas. So basically you can get now antenna separations which are of the order of 100 meters up to antenna separations which are of the order of 30 kilometers from the whole array. The signals from all the antennas are brought over optical fiber. And again, this was one of the first times that optical fiber was used in any radio astronomy observatory. This is, we are talking, stuff designed in the 1980s and built in the 1990s. And they brought to a common place. There's an entire receiver room facility here where the signals are then converted back to electrical, and then all the signal processing, which I have not described in detail at all, is carried out over here. And the entire observatory is controlled by one person sitting in the control room here, who can run everything for the entire array of antennas and monitor everything and run a full observation sequence for many hours of observation. This is just a few more pictures, a view from nearby hill showing the central square antennas. This is a close-up. Now you can see 45 meters is a large size antenna, and the most sensitive electronics sits right at the focus, where you pick up the signal with a feed antenna, which can be a dipole or a horn antenna, and then you give it to the low noise amplifier, which is the one which is really meant to reduce the total noise contribution in the receiver chain. So all of that sits up here, and you need a fairly tall crane, 32 meters height, to reach there for working over there. Just a construction sequence of how the antennas were built. Quite a complicated procedure. We found that out recently because we just last month we had to bring down the first antenna that was raised for carrying out some major repair work, and it's quite a challenge to do this. The basic receiver system is like a heterodyne receiver system, where the dual polarization signals from from the two dual polarized feeds of each antenna are first put through the front end and then brought to the base of the antenna and then modulated onto optical fiber, demodulated in the receiver room, and then digitized and processed in the digital receiver. And with the upgraded system, we are processing up to 400 megahertz of bandwidth from the signal from each antenna. So just again, not to belabor too much, but to just point out that to build an observatory like the Gmrt, there are all kinds of engineering techniques and technologies that have to come together in order to make the observatory into a whole and working in a wholesome manner, and from mechanical to servo to RF electronics to low noise electronics to optical fiber to digital technology, telemetry for the entire array, and the software that goes behind both running the observatory as well as the software that is required for processing the data and getting the final images. So there's some unique features of the Gmrt which I think were landmark, and that's why I'll just spend a couple of minutes talking about them. One was, of course, this configuration, which I very quickly described, the central compact array and then Y-shaped arms. This was chosen very carefully to give optimized sensitivity so that both compact and extended sources, you can make good quality images for all of them. And this choice of observing bandwidths, which I didn't again talk much about, that why were these frequencies chosen? These were chosen to optimize the study of redshifted hydrogen in the universe so that you can probe the evolution of the universe by studying the neutral hydrogen signal from very distant galaxies. And then there was this, which again I didn't talk about, that if you would have noticed that the antenna reflecting surface was almost transparent, but actually, like the Ooty telescope, there is a fine grid of wires over there to reflect the radio waves. So that again, and that whole design was highly optimized so that for the frequencies of interest, you get good reflection of the radio waves, and that without building a solid surface, which makes it much more expensive and heavy, and the entire cost goes up. I already mentioned this. One of the first telescopes to use optical fiber, which was innovation, It posed some problems to us in the beginning till we learned how to master the technique, but it has worked very well over the years, and now all radio observatories use optical fiber for transmitting this signals over long distances. And this it was also one of the first interferometer arrays to support these two modes simultaneously, which again I only briefly talked about. But what this allows you to do is to do an imaging observation in parallel with observing a pulsar or a source of that kind in the same direction of the sky. And this can have very important science spin-offs, which some of our colleagues have exploited. So just in a nutshell, Gmrt over 20 years, the dedication ceremony was on 4th of October 2001 at the hands of Ratan Tata, chairman of TFR Council. And we had the privilege of him gracing the occasion 20 years later when we had the 20 years of celebration of GMRT. Unlike, of course, this being an in-person event, this was an online event due to COVID, but it was a good international gathering that came together to celebrate the achievements of GMRT over 20 years and also to look forward as to what interesting new things may come up, especially with the upgrade having been recently completed. And again, in a nutshell, the GMRT is probably the only facility in India in radio astronomy which is truly of international class, in the sense that it is used by astronomers from all over the world and used in an open competitive mode. So there are proposals that are taken every 6 months, and anybody from the world is free to put in a proposal, and they are evaluated by a evaluation committee and then allotted time on the telescope for observations. And so it's a completely open competitive process. What is heartening is that there's a good amount of time that Indian astronomers are or PIs are able to get on the telescope, and about half of it gets distributed to PIs from all over the world. So to date, I think there are more than 35 countries that people have used the GMRT over the last 20 years. And the competition is fierce. Typically, the facility is oversubscribed by a factor of 2, which means that the number of the total time requested in each 6-month cycle that we get is almost 2 times of the actual calendar time available to schedule on the telescope. So only the best proposals get selected by the selection committee. And what do the people do with this? All kinds of things, from studying the sun, looking for extra solar planets, just like we see radio emission from Jupiter. People try to look for extra solar planets around other stars, to pulsars, to other galactic objects, supernova remnants, microquasars. And today, a lot of the so-called transient astronomy, explosive events, whether it is gamma ray bursts, now fast radio bursts, and all other kinds of transient studies. And then, of course, the what was one of the original main motivations of GMRT, to study neutral hydrogen at different stages of the universe, both in our own galaxy, nearby galaxies, very far away galaxies, the early universe, and so on. And of course, the detailed investigation of radio galaxies. And and then a lot of work has been done in cosmology and the epoch of reionization, of which I talked about the Saras experiment. There's a complementary way of looking for the epoch of reionization signal, which is by using an interferometric array, and that has been tried with the GMRT. In addition, it has also been used to make large-scale maps of the sky. So we talked about all sky survey at 34.5 by the original GT array and at 150 megahertz by the Mauritius telescope. So a similar 150 megahertz all sky survey was made with the GMRT now about 15 years ago, proved to be one of the most sensitive and useful surveys at 150 megahertz published to date, and is really used as a reference for various kinds of studies. Bottom line, of the order of 50 papers in international journals every year based on data taken with the GMRT. There are a couple of other interesting things that we do in addition to studying astrophysical objects, and this is something that colleagues at PRL may be a bit more familiar, which is tracking space probes. And sometimes the world's most sensitive radio telescopes get called upon to do service as ground stations for supporting space missions. And you would have heard that telescopes in US and parts in Australia are used for that. And we worked with NASA and ESA, the two space agencies of North America, of US and Europe, for the tracking of the ExoMars mission, which was a mission to Mars with a lander module. And so the beacon signal that is emitted by this was at 401 megahertz, right in the middle of the GMRT window. And but it's 3 watts from Mars being picked up by the GMRT array. And this was the backend and the processing software is developed in collaboration with the colleagues from NASA. And we actually were able to track. So this is the Doppler of the carrier during the descent phase through the Martian atmosphere. Unfortunately, a bit like our own Chandrayaan mission, this mission was also a failure in the sense that the module crashed instead of making a successful landing, which is something that was picked up by the GMRT when we were doing the tracking. That the signal vanished suddenly, just like we saw it happening on the Chandrayaan when we were watching the TV screens. Um, and so I will. How much time have I used? It's so I will not talk too much in detail about the upgrade, except to mention that every such large observatory often goes through a what we will call a rebirth, where we decide what all features based on technological capabilities can be upgraded and expanded. And once GMRT was working reasonably well, by 2010-11, we started thinking about it, and the proposal was put up to upgrade it. And this was funded in 2012 during the 12th plan, and we went ahead and did this. I won't go into the details of all of this, but the main goal was, you saw that we had these limited bands of observation. Our main goal was to give complete seamless frequency coverage as far as possible, from 100 megahertz to 50. Our original goal was 50, but we ended up close to 100 to 1500 without any gap, and improve the quality of the receivers, of course, with the new technology receivers, and increase the instantaneous bandwidth that we can handle to 400 megahertz from 32 megahertz, a factor of 10 jump. And of course, revamp various other systems which are required to keep the observatory running over the next several years. And all this was a challenge to do without shutting down the observatory to the existing users. So it was done in a incremental fashion, whereby you could still use the observatory while the upgrade was going on. So that was a challenge, but we managed that. And okay, again, I'm probably missing one slide here, which was to talk about what all has been done with the upgraded GMRT. Lots of new results have come. There have been the furthest detection of neutral hydrogen gas so far known, done with the GMRT recently. There's been very high precision pulsar timing results that have come with the GMRT. We are now in the situation of being able to do very long baseline interferometry by running the GMRT in combination with observatories from around the world, simultaneously observing the same source. I'm sorry, I'm missing that slide here. But just to round off, the GMRT has achieved its own set of accolades over the years. And I started by showing you the first IEEE milestone in India for the work by Acharya J.C. Bose. And we are really proud to get the third IEEE milestone in India, given to the GMRT, which was announced in 2020, when we had again a COVID-affected online ceremony in 2021, when the IEEE milestone was actually handed over by the international IEEE representatives to the Indian IEEE representatives, and from then to us in a local small ceremony in NCRA. But this is one of the best recognitions that the Indian radio astronomy has achieved, which basically brings out, if you read that, about the innovativeness and the achievements of what the work done over the many years to build facilities like the Gmrt has achieved for the country. So I'll stop here with just some general summary thoughts. As you saw that within a few years of radio astronomy being born, it was there in India, and it has been built up over the years with the combination of different institutions doing very good work and several landmark achievements, from the simplest experiments to the large, complicated, world-class observatories at the turn of the century. And thanks to these, India enjoys an eminent position in the world in this area of astronomy today. And there are many more interesting developments to look forward to, but I was really running short of time in this presentation to talk about what all we are looking forward to. But I'm happy to take questions if people would like to know. But definitely there is many more interesting developments coming up over the next 10 to 15 years. So thank you so much for your time, and I'm happy to take questions.
Thank you, Professor Gupta, for giving this fascinating talk and highlighting the success story of progress of radio astronomy in India. And you started from radio observations of the sun that began in Kodaikanal to Goribidnur and other sites like Ooty, the ones that were done outside India, that is Mauritius, to the well-known Gmrt telescope. So congratulations to you for this very nice recognition, prominent recognition of IEEE. I think it is very difficult task to cover all these milestones achieved in by India in radio astronomy in one talk, but I'm sure your lucid lecture has, from your lucid lecture, the audience has benefited immensely. So now it's time for question and answer session, and to conduct the same, I would like to invite my colleague, Dr. Manas Samal. Manas, are you there?
Yes, yeah.
Yeah.
Yeah. Thank you, Professor Nandita. Thank you, Professor Gupta, for telling us the history of radio astronomy and encouraging us, particularly how the legacy of India in radio astronomy and achieving the milestone with the Gmrt. So now it's the time for questions. Friends, I would request you to raise your hands through WebEx panel so that we can take the questions and interact with Professor Gupta one by one. So also in between, if there are questions on the YouTube panel, would also take them up. So, so I would request you to please raise your hands to interact with the Professor Gupta. I see Professor Anil Bharadwaj is already in the line. Professor Bharadwaj, please.
Thank you, Manas, and thank you, Professor Yashwant Gupta, for a very excellent talk covering the whole domain of radio astronomy as well as its development in the country. I would like to know that we all know now SK is coming up, right? So anything else beyond SK is happening within the country and worldwide?
Yes, no, sure, and that's a very good question. We all keep hearing about SKA, but SKA is not the be all and end all. There are other plans of growth of radio astronomy in the country that are happening. So, for example, we finished the upgrade of GMRT about 3 years ago, and it's now stabilized and working well. We are already thinking about expanding the GMRT as to what it could look like. So that is one big project that we ourselves are thinking about, to see whether we can make a further improved GMRT, say in 4 to 5 years from now, which would be even more capable, whether it has more antennas at longer distances or it has a new type of technology called focal plane arrays at the focus or other things. There are plans of groups to try and build space-based radio missions, small ones in the beginning with very specific goals, and that will, I'm sure, grow. I'm sure that the SARAS kind of experiment will also see a next phase of improvement and growth. And as I mentioned, which I think some of you may be knowing equally well, is the millimeter wave front, where there is this plan with ISRO leading to build a submillimeter wave telescope, which could be located in the Leh Ladakh region, and there's a lot of excitement about going to those high frequency regimes. And so there is a lot of talk of what we would like to do within the country for the next phase of growth in radio astronomy. Then there is, of course, the SKA. So the SKA is basically the next generation international collaboration, because, if you ask that if you were to build a GMRT today, what would it cost? And that is a cost which is already prohibitive. And if you were to build something 10 times more powerful, for example, no nation can single handedly build now such very large facilities. And so, happening in other branches of astronomy also, optical astronomy, the 30-meter telescope, and so on, that the countries are coming together to pool their resources and their knowledge and talent to build the next generation facilities. And of course, then that has to be in a place which is best suited to locate such a facility. So the SKA is the radio astronomy equivalent of this large international method of doing science. So they call it mega science. Whether that's a good choice of word or not is a different matter. But so we are part of the SKA collaboration, and we have done some of the work during the design phase of the SKA, which finished recently. Construction phase of the SKA is just starting, and there are certain work areas where India has been identified as the country that will be taking an active role in those things. And of course, the science community is gearing up to be able to use a large facility like the SKA when it is ready. So there are all of these things that are on the anvil for the future.
Okay, thank you. And is there any plan to use GMRT also in a big interferometry mode with other stations across the
Yes.
globe?
Yeah, I mentioned it very briefly to do VLBI with the GMRT, and we've already taken the first steps. After the upgrade was over, we needed a few technological things. We needed hydrogen lasers and so on as the stable frequency reference to be able to do international VLBIs. All that is now in place, and we did our first successful VLBI observation runs earlier this year. One with the Europeans, with the European VLBI network, and we did one with the Australians, the Australian VLBI network, and there is one planned with the Japanese. So one of the advantages that India has based on the longitude location is that you can combine with telescopes from either Europe or Australia or East Asia or South Africa. And so for SKA also, which will be located in South Africa and Australia, having India with a frequency which overlaps with the frequency of these different observatories provides a very powerful um, uh, additional capability of the GMRT. So this VLBI thing is going to come up in a long way. In fact, it is part of our cornerstone of partnering in the geodetic VLBI experiment also, which is being led by IIT Kanpur right now.
Okay, great. Thank you.
Okay. Professor R.P. Singh, please proceed.
Thank you, Manas. Thank you, Professor Gupta, for giving such a nice talk. I just wanted to know whether one can measure field correlations instead of intensity correlations using these radio antennas. Field correlations instead of intensity.
You mean voltage correlations?
Not voltage exactly, whether field, I am saying field, like amplitude and phase information, both are there.
Yes.
So, and intensity, you lose the phase information. So can you have field correlation?
Yeah, but I mean, all our correlations are with amplitude and phase preserved. So these are not intensity correlations, what are done in...
When you see the structure, image is final intensity structure.
Yes.
Strength. But I want to see field correlations instead of intensity, I think, not image. Generally, you get processed image. Okay, so that is intensity record. But can you see the field correlations? That's what I'm asking.
I'm not sure I understand that, because finally the physical quantity of interest is the intensity of the radio.
So that's what I'm saying. You are measuring intensity. Can you have field correlations? Because in
No,
radio
but
you can
in
measure
order to
phase.
get that
Radio waves,
intensity,
it's easy to measure phase.
but in order to get that intensity, what we measure is the field correlation, in the sense that we are taking the voltage from individual antennas and correlating that. So the amplitude and phase of that voltage is preserved and available, and both give complementary information about the structure of the source. I'm not sure if I'm addressing your question, but
So
the way the observations are done and data is taken, it is both amplitude and phase of the signal are kept, and they are used to give the full information about the source.
so whether one can have that data where you have this voltage records of field, I think.
Yeah. So that is not very easy, because that recording that voltage and saving it means sampling it at the Nyquist rate, and that is prohibitively expensive. So, for example, just to give you an idea, the total voltage data rate from 30 antennas of GMRT today is 20 gigabytes per second. So, if I have to give you that raw voltage, I have to record data at 20 gigabytes per second, which is not possible, practical. I mean, I may be able to do it for a few seconds, maybe a few minutes, but if you want it for hours, it is not practical. So that is why the interferometry technique does some amount of the online processing of the voltages, saves the amplitudes and phases of the correlated products from the individual pairs of antennas, integrated over a certain duration. Those are then used for the imaging. Now, for the other experiment, like the VLBI that we were just now talking about, where you are going to take data from faraway located antennas and you can't bring it together and correlate immediately, though today it's possible with long distance optical fibers, then you record that raw voltage locally, then you transport it over to a common place and do this. For those raw voltage recordings are possible. So that is a mode which is used relatively infrequently because of the prohibitive cost of data storage, but in principle it is possible.
So if I submit a project, I can
Yes,
get those
you
records.
can. Yes, so there is a very special mode of observation where you can request that I want the voltage data from all 30 antennas to be recorded and made available to me. We support that mode, but if you ask, give me for 24 hours, we may not be able to
Not
support it.
24 hours,
Yes,
just a
yes,
small time.
yeah. So yes, that mode is available, and for special observations, scientists do use that mode.
Okay, thank you very much. I want to get this information for detecting orbital angular momentum of these radio waves. Some like rotating neutron stars, they are supposed to emit waves with helical wavefront and having orbital momentum. So
Okay.
looking at the field correlations, one can check whether it's there or not experimentally.
Sure. No. So please have a look, and please get in touch with me if you want to understand specifically the capabilities that are available, and then you can put in a proposal based on your understanding of what is possible and what you need.
Okay. Thank you.
Okay. Now I would like to invite Professor Ashok Ambastha. Professor Ambastha, please. Okay. Otherwise, Professor Sachindra Naik, you may continue. Then Professor Ambastha may join later.
Okay, so thank you, Yashwant, for a nice overview of radio astronomy in India, development of telescopes and everything here. And also congratulations for leading a world-class instrument or observing facility.
Thank you. Thank you,
There.
Sachin. Yeah.
Okay. So my question is partly asked by Professor Anil Bharadwaj. Basically, this Event Horizon Telescope, basically the baseline was increased to go for higher and higher sensitivity. So during that period, was there any discussion or attempt to include GMRT or couple of antennas from GMRT in that telescope so that would have been better, or is there any such discussion, or the location is not suitable for that kind of study, or any comment on that?
Yeah. So basically, the Event Horizon Telescope frequency of operation is much higher than what we use. It's in this millimeter wave astronomy regime, which is one area of astronomy where we are not very much up to this thing. So And again, it's the same question, that resolution, that lambda divided by d. So there, although you are having baselines, antenna separations which are intercontinental, that so if you know that the telescopes involved in the that experiment were located on different continents, and that is really the VLBI technique. But even then, you have to go to the lowest wavelength, the smallest wavelength that radio offers you. They have to go to 100 of gigahertz or higher, without which you cannot get enough resolution to get that the shadow of the black hole resolved. So if you try to do that at meter wavelengths, getting at that frequency.
Okay, okay, thank you.
Bires, you may ask your question.
Yeah, thanks a lot, Yashwant, for a very informative talk. So my question is very short. About one thing is about VLBI. That is there any plan that the VLBI will be a regular observing mode with the GMRT in future?
Yes.
Okay.
Very much. And so if you would have, I don't know if you follow the every 6 month updates that we give about the capability, but the last update for which the proposals were due couple 10 days ago was the last date for the proposal submission. That one now allows the VLBI mode to be available for use by any user. And even right now, we are discussing with these different VLBI networks. In fact, we have a call tomorrow with Australian colleagues to plan for joining in the Australian VLBI observations. We have a discussion due with the European VLBI network for joining the EVN as a member. And so soon, once all these things happen, the VLBI observations will be a regular part of the GMRT's schedule and the plan, and based on the international proposals that are put together, which ones are suitable for GMRT to join.
Okay, thank you. And I have another short question, second question. This is about eGMRT you spoke about. That so is there any plan or definite plan that how many antennas will be put up and what will be the baselines?
No, so that discussion is still going on because there are different pros and cons of what is going to be scientifically more rewarding, keeping in mind the international situation. So one is, of course, more resolution. So you would say just put more antennas at longer baselines to get higher resolution. That is not as straightforward as it sounds, because you have to worry about at the low frequencies that we work, will you be confusion limited? If you are, then does it make sense to have a much higher resolution? Number
Okay.
one. Number two, there is a competing thing that do you want higher resolution, or do you want the ability to have a better capability to see diffuse emission? If you want the latter, then you want more antennas at shorter spacings rather than at longer spacings. There's a third competing thing which says, well, do you want a higher survey speed or capability? So then instead of investing in more antennas and more baselines, should you invest in what is called a focal plane array feed, whereby you can get a multi-pixel feed at the focus of each antenna, and you can cover a much larger area of the sky plane while pointing the antenna in the same direction. So these are these, now you can see these are all
Yes.
completely contradictory or really very different requirements, both from the view of what science it will allow, and therefore which is the best one, and the technologies that are involved and the effort that is involved. So this discussion is going on. It will take some more
Okay.
time before I think some
Yes.
final consensus emerges.
Okay. Thanks a lot.
Okay. Professor Ombasta, are you around? Okay, there are two questions posted on the chat box from our YouTube viewers. One question by Alkas Shekhawat, and she is asking why the antennas are placed in Ycef configuration.
Yeah, so I didn't have time to go into the details of how the aperture synthesis mode works, but basically the idea is that you want, since you don't have the full dish, the full aperture, you want as many locations where distinct baseline pairs of antennas. If you think of it as a two-dimensional vector on the ground, you want all different two-dimensional vector positions, as many as possible, to be covered. There's an additional factor here that as the Earth rotates, the orientation of the baseline changes with respect to the source. So you have to factor that in when you do that calculation. And so there is a way of simulating that if you have n antennas, and in our case, say n is 30, and you want to you place them over a certain region, then in what way should you optimize that placement so that you can get the maximum effect of that resolution that you are after. And it turns out that this Y-shaped structure is one of those configurations which offers you close to the optimal choice. There are others that are possible. For example, the SKA has gone in for some kind of what is called a spiral geometry of spiral arms as compared to pie-shaped arms. And so there are one or two configurations which turn out to be the optimal ones from this exercise of maximizing the amount of coverage that you can get from a limited number of antennas.
Okay. So there is a question by Kusakar Upadhyaya asking, can you please give some brief idea about the technology used in the Gmrt backend?
Okay, that's a very good question, and that's something I could easily talk to you for 15-20 minutes, because that has been a lot of the work that I have done over the years. But the current Gmrt backend, as you saw in my thing, that the signal from the antennas of 400 megahertz bandwidth is digitized, and 30 data streams are processed. So in the early days, we used to do it with discrete digital signal processing chips and boards and so on. Around 90, 90, we decided to move over to what is the equivalent of software-based computing. If you know software-defined radio and all other things where you say, look, any heavy signal processing computational job, can you move it to a compute cluster? And so we did this, and a lot of the signal processing, after the data is digitized and synchronized, you have to synchronize the data trains from all the 30 antennas, align them, and so on. The processing is now done today in what I would call a mini high performance computing system running at the observatory. But it's a real time system. It is continuously ingesting 20 gigabytes per second of data, doing all the calculations and putting out the numbers. So we use GPU enhanced computing in order to do this task, to implement the algorithms, which I didn't have time to explain how the interferometry algorithm is implemented or how the beamformer algorithm is implemented. But basically, that's a direction in which the backend processing has gone. I don't know if that answers the question adequately enough, but if you have any further queries, just feel free to write to me about it.
Okay. Please, Kusakar, take a note. If you have any doubt, you can write to Professor Gupta. So moving on, I see hands been raised by Professor Santosh Badawale. Professor Badawale, please proceed. You are muted.
Yeah, am I audible now?
Yes.
So thank you, Professor Gupta. It was really an excellent talk, giving overview of the radio astronomy as well as GMRT specifically. I have a couple of questions. One is a technical and another one is a slightly logistic. So in terms of technical question, for single dish of GMRT in a photometric mode, what will be the kind of sensitivity which can be achieved in terms of a Millijansky level for source?
It depends on what you're doing, how long you're integrating, but the raw number is 0.3 degree Kelvin per Jansky that is the thing you will get from a single antenna. And if you have a 1 Jansky source, it will give you 0.3 degree Kelvin of signal temperature. And depending on which frequency you do it, the noise temperature can vary anywhere from, say, 70 degree Kelvin at the L band highest frequency to several hundred degree Kelvin at the lowest frequency. So if you are wanting to detect a source, you will have to integrate a long duration in order to bring down the noise to be able to see the source. I'm not sure what specific thing you had in
so,
mind.
so that is where I'm sort of coming. That typically, like for example, I'm working on a kind of microquasar sources. So now the microquasar, I mean, continuous radio monitoring, a kind of daily radio monitoring of the sources is sort of very important. In fact, we are having some very interesting results with AstroSat now, for which we are looking for some radio, some simple flux data, whether available or not, but we are not finding that. So in that context, we are wondering, I mean, suppose if we have to kind of put up that kind of program where logistically, whether it would be feasible to kind of allocate one dish for this kind of monitoring, which will take up a daily or maybe at least alternate day of most of the list of the sources monitored or something like that. I mean,
Unfortunately, that is one mode that GMRT, I mean, in principle, it is possible the way the instrument is designed, but in practice, as a policy,
yeah, so that's it.
the time allocation committee, you will find it very difficult to convince them,
Okay.
because the question will be, let's say you take one or two antennas for monitoring something. The question is, what other science program you run with the remaining 28 or whatever number of antennas are available at that time, that is going to be affected, because that same person would have said that, look, if you had given me all the antennas, I would have got the optimal result. So this mode, there have been such queries. We tend to discourage that mode where, on the other hand, mode where the array is split into two subarrays or three subarrays, where the different sets of antennas are doing something slightly different. Maybe they're observing the same source at different frequencies, for example, which is scientifically useful. They could be observing three different sources under the same observing program. Okay, so but then your thing is that you want long time cadence.
Long time.
So that is not. I
So
mean, if you wanted to monitor 30 different quasars simultaneously, for example,
yeah,
but let's say for an hour each or 2 hours each every 1 week or
something like
something,
that.
then you can use it in the subarray mode. But it depends on what time resolution you will want for that monitoring. Probably not very high, right?
So this was in the context. I mean, for example, the other question was like, it was not single dedicated, single proposal, but let's say it's kind of concurrent moving program. So rest of the antennas will anyway will be dedicated for or using their own other observations, but maybe one or two antennas which are kind of
No. So,
used
like I
for
said,
this.
the problem comes out of whose proposal do you take
Yes.
away the two antennas, mine or yours or somebody else's, right? Because anybody will say, give me as many antennas as possible
Yeah.
for my best science. See, what people do is, if the number of antennas is sufficient, you reduce the time duration, so you reach the
Yeah.
sensitivity quickly. But so that's a problem, that this kind of observation
Yeah.
that you are talking about is, policy wise difficult to support.
Yeah. So that's what I mean. I just wanted to
Yeah.
sort of have your view, so I can understand.
You can give it a try. You can see
Yeah, no, I mean, so, so that's what I mean.
what the
Before
review
directly
committee,
putting
what the
proposal, I
committee
was
says
anyway, I mean,
about
so
it.
we had been
Yeah.
thinking a
Yeah.
little bit in that direction. So that's what I thought.
Right.
It's a nice
No, but
opportunity to have your
if the
view.
science goal,
Yeah.
is very compelling, maybe the committee may come with some
Mm.
way of solving the problem. I mean, they will probably transfer the problem to us, that can you schedule this without causing too much trouble. But
Yeah, yeah.
you can try it and see.
Sure. Thank you.
Okay. A question by Prachi Pajapati asking like interferometry techniques in space, and what are the challenges to start with, and what are the plausible solutions to overcome them?
Okay, that you've asked a very big question. Radio interferometry from space, though actually you will be surprised, it has already been done. Okay, there have been at least a couple of missions, where an antenna, a radio antenna, has been launched on a satellite, and you should go look up the project called Radastron, or Radio Astron, which was run by Russia, where actually we contributed. So one of the receivers in that was at 300 megahertz. That system was designed by Gmrt engineers. It was space qualified at SAC Ahmedabad and sent and integrated into the the mission in Russia. But just to tell you that that mission flew after a lot of delays, and it was there in the sky for over 5 years. It just sort of ran out of its basic capabilities about 2 years ago. And what happens there is that antenna is a single antenna, not very large. It's only of the order of a meter or two. As you can imagine, you can't today take up much larger antennas into space. So it was taken up, just like an umbrella and then unfurled. And you would have seen JWST, the mission, doing all kinds of things like that. So that antenna is looking at the same object as the ground-based antennas are looking, and the data is again brought together, collected, and then correlated and analyzed to get very high resolution images, where now the distance is 10,000s of kilometers as compared to 30 kilometers of Gmrt or few thousand kilometers of continental baselines. So it has been done. Some interesting science results have been produced. Some of our colleagues from India, including from NCRA, were part of some of the experiments. And there is talk of follow-up space VLBI missions, but nothing very concrete right now on the anvil. There's also talk of small microsatellites with small antennas floating like a constellation in space. There are lots of ideas, but finally, what works practical is a more challenging thing.
Okay. So I don't see any hands being raised or any questions posted in the YouTube. By any chance, if I missed anybody, please, you unmute yourself. You can ask your questions.
I think Professor Ambasta has, I think he's unmuted also, and he has also posted a question.
Okay, really? I don't see in the chat box.
Yeah, there is. I can see his question.
Yeah. Okay.
He says, my question is about any future space missions in radio. Okay, so I think that I sort of briefly answered just now. Then he says one uses space missions for X-rays, UV, they as optical. Yeah. So I think that's the Professor Ambassa. That is what I said. What you expect to gain from a space-based radio mission is just this longer separation of the antennas. So you can have antennas separated by distances which are not limited by the diameter of the Earth, which is the limit for any ground-based observation, much less than the diameter of the Earth in practice. But so that is the gain that people are talking about if it becomes a practical issue.
Okay. So before we move to the...
I have one small question.
Okay, please go ahead.
Yes, so Professor Gupta, you talked about Mauritius telescope. Other than going to the southern hemisphere, what were other advantages of going out of India to cover this?
No, so I'll tell you what happens. In India, we have two problems which hamper radio astronomy, which have been challenges for us. And I think there's one more question in the chat box about which is relevant for that, but I won't touch upon it unless you really ask me. But one of the problems is the biggest enemy of radio astronomy is man-made noise. And man-made noise is directly, except for noise coming from satellites, man-made noise is directly proportional to density of human population. Okay, and as you know, we don't do very well over there. So people want to build radio telescopes. If you could build one in the desert of Rajasthan, people would want to do that because very few people living there, very few mobile towers, very few TV transmissions. So the world that's why the SKA has chosen sites which are in the semi-desert regions in Western Australia. There's this big Great Australian Desert, as you know, which occupies the western half of Australia. So on the edge of that, and in the northern part of South Africa, which is again a semi-arid region with very limited few. So there, the population density is measured in 1 person per square kilometer, half person per square kilometer kind of a number, which is unimaginable in our country. That is one of the major things. The other major thing is that there is the interaction of the radio waves with the ionosphere, which distorts the signals. That depends on the level of ionospheric activity, which varies over different places of the Earth, depending on where the the geometry is, which is called, there's a specific term for it, and and India is not very well suited for that. In fact, the reason why GMRT was moved to the northern, I mean not northern, meaning it is middle of India, was that you could not put it at 10 degrees south because ionosphere is much more active over there, for example. So that's one of the reasons why building much more bigger sensitive facilities is going to be harder, and joining the big international projects and going along and getting the benefits both in terms of the science and technology is one of the options that we are also looking at very carefully.
Or then one can think of the space-based things if one wants
Yes,
to.
but the space-based thing is very expensive for for large antennas like radio antennas to do this. I mean,
Okay.
it's still a few generations away for a general, maybe a few niche experiments can be done.
Okay, thank you.
Professor Gupta, I hope you have few minutes to spare because I see few questions pop up in the chat box.
Yeah, that's okay, fine.
Okay, a question by our colleague Mithun asking, radio data, raw data rates are very high or very large. Then how these are downloaded from space for VLBI?
Yeah, so that space VLBI is a very special experiment, limited bandwidth, and therefore smaller data rate. And what happens in all of these is whenever you have a large data rate, you do the two things. That is, you run intermittently. So you run for 5 minutes, 1 hour, whatever. You collect a large amount of data, and then you slowly send it down on a slow link if you have a slow link to send it. That means that telescope is idle for that time when that data is being emptied out and sent. So that is one way in which such space VLBI operations happen. So they are limited. It's not like that GMRT handles 24/7 the data coming in. It doesn't stop because the data processing has been built that way. But when we do VLBI observation, we have to record the raw data, as was asked by somebody else also. That I can't do continuously non-stop. I have a limit. After that, I have to stop. The data has to be copied out, sent somewhere, and then only can I do a next VLBI observation.
Okay. So one of our colleague asking, like Sandeep Raut asking, how are radio signals transferred through optical fibers, and what benefits does it have compared to, say, for example, the easier transferring of voltages?
Oh, as compared to?
Voltages.
Well, it's voltage only, but I'll tell you what. So, see, there are two ways. I mean, there are 3 ways in which you can send a voltage signal, right? You put it on a coaxial cable and send it, right? Or you modulate it onto airwaves, AM modulation, FM modulation of a carrier wave, and you transmit it, and then you receive it, and then you decode it. Or you modulate it onto an optical fiber signal, right? And again, it's either amplitude modulation or depending on in communication technology, you have various phase shift modulation, FSK, blah, blah, FM and all that. But the simplest modulation scheme is AM modulation. So you have a carrier. In the case of optical fiber, that carrier is the light wave signal. You modulate the amplitude of that based on your RF signal of interest, and you transmit it. Now you ask, what's the advantage? So the optical fiber link is much more secure. It is so, for example, if you're transmitting with an RF carrier, if the RF carrier suffers any phase change or any amplitude drop, when your signal fades when you're listening on your phone or on your radio or whatever, that fading and problems are due to signal transmission issues, right? But if you were connected on an optical fiber link for your data net, the connectivity, say, between your office and your home or somewhere, you will find that there's a very stable connection. So the optical fiber gives you the most stable and good quality connection. We can control the phase changes of the optical fiber signal by burying it under the ground, which is what we do. The optical fibers are buried 1.5 meters below ground from every antenna to GMRT, and so it just provides you a much better way of transmitting. Today, of course, we transmit still the analog modulation. What people are doing in modern observatories, you digitize the signal right at the antenna, and you then transmit the digitally modulated signal, just like an Ethernet connection. So when you get your Ethernet over optical fiber, it's like getting an Ethernet connection from the antenna, except that the Ethernet is not 1 Mbps or 1 Gbps. There is 100 Gbps or something like that.
Okay, so there is a question by Vaibhav Dikshit. He's interested to know, as you know, that we are seeing increased use of radio bands for communication purpose, like mobile, FM, and other such gadgets.
Yeah.
And he interested to know how the noise originated from these sources are fitted to get meaningful scientific results.
Yeah, no, that's the most challenging questions to answer. But you picked a very important point that, like I said earlier, our biggest enemy is man-made transmissions, and we have different ways in which we handle it. One is, of course, that we design our electronics so that we can try to avoid this, either by putting filters at the right frequencies or by doing other kinds of clever signal processing techniques in the signal that is being processed. However, if the interfering signal is so strong that it saturates our receiver, makes it nonlinear right at the front. Remember, we are looking at very, very faint signals, so our receivers operating levels are very low. So these strong signals can easily make it nonlinear. Then we have to do something right at the source, which means that you try to find who's transmitting and work with them to reduce their transmission or shift them to some other frequency or not have them come there. So there are various things that we do. I won't go into the details. We try to get mobile phone operators to not operate at 850, 900 megahertz and operate at 1800 megahertz. We try to avoid power lines, new high tension power lines to be built which go through the array. We have a control on what kind of industry comes up in a 30 kilometers zone around Gmrt. They have to get a no objection from Gmrt to put up any industry, and we check what kind of equipment that industry is going to put. Is it going to be equipment that produces sparks? We don't allow petrol engines, spark-driven vehicles in the observatory. Only diesel engines which have no spark plugs are the. So there are there are various these things. We screen the computers that we buy. We screen the air conditioner units that we buy. We screen the LED lamps that we buy and install at the observatory so that they don't produce interference. And we take steps to reduce the interference from all of these, which you think is, you would say, where is this interference? But all of these things produce EMI signals, which are harmful to the observatory.
Okay, so we already had a lot of discussion. I just want to conclude by asking one question, that how can our students or postdocs would benefit from the, knowing about Gmrt data reduction processes, and how can they collaborate in what capacity?
Good. I think Viresh and others have to step in. These are the people who understand what we do, and you should set up a group. I know there are at least a few faculty members now who have enough understanding and interest of the radio astronomy and the working of GMRT. And we do, by the way, there is a school that we conduct in the summer. Of course, the COVID has created lots of problems, but I think we'll be again resuming regular things, which is meant for early PhD career people for who are not radio astronomers but are working in a field where the radio astronomy data will be useful. So we have a training school in the summer, and I think Viresh will be knowing about that, the summer school, which welcomes MSc, PhD students who are not whose core area is not radio astronomy but has an overlap. And we are always happy to have visitors to come and visit in general, just to understand. So if you were to organize a visit from interested scientists from PRL, we would be more than welcome to host them. And then you can have more specific, detailed follow-ups on specific topics.
Okay. Thank you, Professor Gupta, for answering all the questions from our WebEx panel members as well as taking up the YouTube questions. It is indeed a great pleasure to listen and hear you and see all the historical achievements that India has achieved in the radio astronomy domain. So now I would like to invite my colleague Dr. Bhala to propose vote of thanks. Dr. Bhala, over to you.
Thank you, Manas. Thank you, Professor Yashwant Gupta. You have taken us through a journey of how radio waves were used for science in India and the development of world-class facilities. I'm sure it is just a matter of time that radio astronomy will lead to many new discoveries. We ourselves do astrochemistry in PRL, so we are looking forward for more contribution from the field towards the molecules that are in this space and the conditions that they are being made more complex from simple molecules. So thanks once again, Professor Yashwant Gupta. And thanks to the PRL director and Dean PRL, as well as to the Vyakhyaan committee, Professor Dita, Professor Lokesh, Dr. Manash, and to all the team members. With this, we conclude today's Amrut Vyakhyaan, and please stay tuned for the next Vyakhyaan next Wednesday at 4 p.m. Thank you. Thank you, one and all.
Okay, yeah, thank you. Thank you so much for the opportunity. It was great to interact with everybody.